Imagine a room where the temperature is colder than deep space, colder than the surface of Pluto, colder than anywhere else in the entire solar system. And in that room, scientists just did something they have never done before on American soil. They took a machine that behaves like nothing else in physics, and they wired it directly into the fastest scientific supercomputer in the United States. Not in a lab experiment, not in a simulation. In real life, this week, at a government facility in Tennessee. And if this connection works the way scientists hope, it could change how we discover new medicines, new materials, and new forms of energy, years earlier than expected. But here's the catch. Nobody is completely sure yet how far this new machine can actually go. Stay with me, because by the end of this video, you will understand exactly what just happened, why it matters, and why some scientists are excited while others are choosing their words very carefully. Let's start with the giant in this story. Its name is Frontier, and it lives at Oak Ridge National Laboratory in Tennessee, a research facility run by the U.S. Department of Energy. Frontier was the first supercomputer in history to cross the exascale barrier, meaning it can perform more than 1 quintillion calculations every single second. To put that in perspective, if every person on Earth did 1 calculation per second, all 8 billion of us together, it would take the entire planet more than 4 years to do what Frontier does in a single second. Frontier is built from over 9,000 computing nodes, each one packed with AMD processors and AMD Instinct accelerator chips, all wired together with roughly 90 miles of networking cable and cooled by thousands of gallons of water every minute, just to keep it from overheating. This machine has been used to simulate nuclear fusion reactions, model the spread of diseases, and even train massive artificial intelligence systems. Frontier is often described as the world's most powerful supercomputer, built specifically for open scientific research, and for years, it has represented the absolute ceiling of what classical computing could achieve. But even a machine this powerful has a wall it cannot climb over. There are certain problems in chemistry and physics that Frontier, no matter how many processors you add to it, will never be able to solve efficiently. Not because engineers didn't build it well enough, but because those problems are built on a foundation that classical computers were never designed to handle. And that wall is exactly why scientists just plugged something completely different into Frontier's home. Something that doesn't calculate the way normal computers do at all. To understand what that something is, forget about computer chips for a second. Think about flipping a coin. A regular computer bit is like a coin that has already landed. It's either heads or tails. 0 or 1. That's it. Now imagine a coin that is still spinning in the air. While it's spinning, it isn't purely heads or purely tails. It exists in a blurry mix of both possibilities at once. That spinning coin is roughly how a quantum bit or qubit behaves. And when you link many of these spinning coins together in the right way, they can explore an enormous number of possible answers to a problem simultaneously, instead of checking them one at a time like a classical computer does. For certain types of problems, especially ones involving how molecules bond together or how electrons behave inside new materials, this gives quantum computers a theoretical advantage that no amount of classical horsepower can match. That's the theory. The challenge has always been building a real quantum machine that is stable enough and useful enough to actually plug into real scientific work instead of staying locked away as a lab curiosity. And this is where the actual news comes in. On June 16th, Oak Ridge National Laboratory switched on a new quantum computer named Pathfinder, sitting inside a specially built facility called the Translational Research Capability Building. Pathfinder is a 20-qubit system built by a Finnish company called IQM Quantum Computers, and this marks IQM's very first quantum computer installation anywhere in the United States. It also happens to be the very first quantum computer that Oak Ridge has ever purchased commercially and installed on site, right alongside Frontier. IQM's co-founder and CEO, John Gutz, said something that captures the whole point of this project. He said that quantum computing only becomes genuinely useful once it is working inside real computing infrastructure, and that there is no better place to prove that than at a facility like Oak Ridge. Travis Humble, who directs Oak Ridge's Quantum Science Center, added that having this quantum computer physically present on campus has already sped up the lab's efforts to merge it with their world-class supercomputing systems. Now here's where it gets genuinely interesting, and where a lot of the hype around quantum computing tends to fall apart if you look closely. Pathfinder is not connected to Frontier through some flashy new invention. It's connected through something almost boring by comparison. The same job scheduling software called Slurm that Oak Ridge's staff already use to assign tasks to Frontier's classical processors. In other words, when a researcher submits a scientific workload, the system can now decide task by task whether a piece of that problem should be handled by Frontier's classical chips or handed off to Pathfinder's qubits, all within the same facility, using the same operators, with all the resulting data and intellectual property staying entirely under Oak Ridge's control. That last detail matters more than it sounds. Most people who have used a quantum computer so far had to do it remotely, sending their computing jobs over the internet to shared machines owned by outside companies. That approach creates delays, scheduling bottlenecks, and messy questions about who owns the results. Having the quantum machine physically on site in the same building, running on the same scheduling software as the supercomputer, removes almost all of that friction. But building that connection in the physical world turned out to be its own enormous engineering fight, and it's a fight most people watching this story from the outside never even hear about. Superconducting qubits, the kind used inside Pathfinder, are made from tiny circuits that have to be cooled to a fraction of a degree above absolute zero, colder than outer space, to strip away electrical resistance and keep the qubits in their fragile quantum state. Oak Ridge uses a specialized cooling system with helium compressors to bring the machine down to around 4 Kelvin, and then an even more precise gas handling system to push the actual superconducting components below 10 millikelvin, which is roughly 1/100th of 1 degree above absolute zero. The building housing Pathfinder was constructed with the ground floor isolated from the rest of the structure, specifically to control vibration down to a level as small as 250 microinches. Because a vibration that a person would never even notice can be enough to disturb a quantum state and ruin a calculation. Engineers who worked on a nearly identical 20-qubit deployment noted that quantum hardware demands far stricter control over vibration, temperature, and electromagnetic noise than any classical computing node ever has. That daily automatic recalibration has to be built directly into the job scheduler, and that redundant power and cooling are simply non-negotiable. None of this sounds glamorous, but it's the invisible plumbing that determines whether a quantum computer actually works reliably inside a real research pipeline, or just breaks down every few hours in a lab somewhere. And that raises an uncomfortable question that not everyone wants to answer honestly. 20 qubits. That's the number sitting at the center of this entire announcement. And if you've followed quantum computing news even loosely, you might be wondering if that number sounds a little small. It is. Some quantum computers built by other companies already operate with over 100 qubits, and even those systems are still considered far too small and too error-prone to solve most of the practical, real-world problems that quantum computing is ultimately promised to unlock. So why would one of America's top research labs get excited about a 20-qubit machine? The honest answer is that Pathfinder was never meant to be the machine that cures diseases or invents miracle materials on its own. It was built to answer a much narrower, much more practical question. Can a quantum computer physically survive and reliably operate inside the demanding environment of a world-class supercomputing center, wired into the same workflow as classical machines? IQM's Radiance architecture, the same design used in Pathfinder, uses a specific layout of superconducting qubits arranged in a square grid with tunable connections between them. A structure deliberately chosen because it's compatible with a leading error correction technique called the surface code, which is widely seen as one of the most promising paths toward building a genuinely fault-tolerant quantum computer somewhere down the road. In plain language, Pathfinder isn't just a quantum computer, it's a rehearsal for a much bigger quantum computer that doesn't fully exist yet. And here's the part where I have to be straight with you instead of feeding you hype. Experts genuinely differ on how soon quantum computers will deliver a clear, undeniable advantage over classical supercomputers for real scientific problems. IBM has publicly stated its roadmap targets a fault-tolerant quantum computer by 2029, meaning a machine advanced enough to correct its own errors reliably during a calculation. Other companies and researchers have offered different timelines, some more optimistic, some more cautious, and some reports openly acknowledge that predicting the exact moment of quantum advantage has proven far harder than the industry originally expected. So if anyone tells you quantum computers are already outperforming supercomputers on real scientific problems today, be skeptical. That's not where we are yet. What Oak Ridge just proved is something more modest, but arguably more important for the long run. That the physical, logistical, and software infrastructure needed to run quantum and classical machines side by side as one unified system actually works right now in a live research environment. And Oak Ridge isn't attempting this alone in a vacuum. This is part of a much bigger coordinated push happening across the United States and internationally, all racing toward the same underlying goal. Just months before Pathfinder came online, IonQ announced a partnership with South Korea's National Supercomputing Center to plug quantum hardware directly into that country's national computing backbone, using a new connection technology from NVIDIA. Around the same time, NVIDIA also powered the launch of a massive research supercomputer in Japan, combining superconducting, neutral atom, and photonic quantum processors, all working alongside classical GPUs at once. IBM and MIT recently launched a joint computing research lab specifically dedicated to tightly integrating quantum processors with high-performance computing and AI systems. And closer to home, the Pittsburgh Supercomputing Center is now building its own hybrid quantum classical machine, funded by a $5 million grant from the National Science Foundation, with construction beginning later this year. What all of this tells you is that no single country and no single lab believes it can win this race by building quantum chips in isolation. The winning strategy, at least for now, is building the bridge between quantum and classical computing before anyone fully knows which type of quantum hardware will ultimately come out on top. It's also worth being precise about one detail, because accuracy matters more than a flashy headline. When people call Frontier the fastest supercomputer in America, that title depends slightly on which benchmark you're measuring. On raw, traditional computing performance, another Department of Energy machine, El Capitan at Lawrence Livermore National Laboratory, currently holds the very top global ranking. But Frontier remains widely recognized as the most powerful supercomputer in the world, dedicated specifically to open scientific research. And on mixed precision benchmarks closely tied to artificial intelligence workloads, Frontier has posted some of the fastest results ever recorded. So when this story gets described as America's fastest AI supercomputer gaining a quantum partner, that framing reflects Frontier's role and reputation in the AI and open science research world specifically, not a claim that it beats every supercomputer on every possible measurement. Small distinction, but the kind of distinction that separates an honest tech story from a misleading one. So what actually happens next? Now that the wires are connected and the cooling systems are running, Oak Ridge's research teams say they're now focused on developing new methods and software tools to explore practical applications in materials science, chemistry simulations, and artificial intelligence. 3 fields widely considered among the most promising areas where quantum computing could eventually offer a genuine advantage over classical methods alone. Materials science, because simulating how atoms bond together to create a new battery material or a new superconductor is exactly the kind of problem quantum mechanics is naturally suited to represent. Chemistry, because modeling how complex molecules interact, the same kind of modeling used in drug discovery, becomes exponentially harder for classical computers as those molecules grow larger, while quantum systems may scale far more gracefully. And artificial intelligence, because researchers are actively exploring whether certain narrow pieces of machine learning workloads could eventually be accelerated by handing them off to quantum hardware, the same way Frontier already hands off certain calculations to its own specialized processors. None of these applications are proven breakthroughs today. They're active research directions. But they're the reason a 20-qubit machine, however small it sounds, is being treated as a serious milestone rather than a publicity stunt. There's one more thing worth understanding before we wrap this up, because it changes how you should think about the entire story. Pathfinder isn't even Oak Ridge's first attempt at this kind of integration. Last September, the lab quietly installed a much smaller 6-qubit quantum computer, built by a company called Quantum Brilliance, inside its computing facility, largely as an early experiment. Pathfinder represents the next, much more serious step up from that first small trial, which tells you this wasn't a single dramatic announcement out of nowhere. It's a deliberate, gradual build-up, one careful step at a time, toward a future where quantum and classical computers might not be treated as 2 separate categories of machine at all, but as 2 halves of a single unified research tool. If you've made it this far, you've essentially just learned something that most people, scrolling past a flashy headline, never actually understand: the real difference between a quantum computing announcement that's mostly marketing and one that represents genuine, careful engineering progress. This was the second kind. If you found this breakdown useful, consider subscribing, because we cover stories like this, real developments in AI, computing, and science, explained without the exaggeration. What happened at Oak Ridge this month isn't the moment quantum computers took over. It's something quieter and honestly more convincing. It's the moment American researchers proved that 2 fundamentally different kinds of machines, one built on certainty, one built on probability, can finally sit in the same room, share the same software, and start learning how to work as one. Whether that partnership eventually cures a disease or designs a material we haven't imagined yet, nobody can promise you today. But for the first time, the question isn't purely theoretical anymore. It's running right now in a cold room in Tennessee, one calculation at a time.